Okay, let's get started. Okay, the first couple of pages is again the review of BPSK block diagram, also the QPSK, right? And what we are trying to understand now is part of the midterm exam, right? In the midterm exam, we have the same block diagram, like a transmitter and receiver. The only difference is that we have a phase at the receiver, right? That was the only difference in the midterm. And that's what we're going to talk about today, right? So remember this BPSK, the block diagram, TX, transmitter, receiver. Also, this is a QPSK transmitter and receiver. Okay? So we have I channel here, Q channel. Each one is same as a BPSK. So that's why we call that the QPSK transmitter. Inside, we have a 2 BPSK with transmitter in parallel. One BPSK is using cosine as a carrier. The other BPSK block uses sine as a carrier. And you are going to add it all together because the cosine and sine are orthogonal. Now at the receiver, we are going to multiply cosine into the I channel because I channel we multiply the cosine. So we are going to multiply cosine again. Right? And in the Q channel, we use a sine as a carrier, same way. So it's like a BPSK receiver, one here, another BPSK receiver here. The one use cosine, the other uses sine, and we combine them together eventually. So that's what we have in the QPSK receiver. Okay? This block explains the Costas receiver. So some of you remember this name, Costas receiver, right? This is a block diagram Costas receiver. And when you look at your textbook, you will see this figure, and you will see this Costas receiver when you learn the DSB. You remember DSB? Double sideband? That's part of the amplitude modulation in analog, right? So when you learn the analog communication, DSB SC, right? Double sideband suppressed carrier. So when we learn this, you will see this block diagram in your book, right? So that is Costas receiver. So let's take a look at this one, right? This is a receiver, as you see here. This is receiver. So you're going to receive some DSB-SC signal coming into the receiver. So before that, let's go all the way back to the transmitter first. So what does the DSB-SC transmitter look like? Let's go back to analog. So we have message, original message. That can be your voice or any analog message. This message will go into what we call is a product modulator or mixer, and we're going to multiply our carrier, CT. And this carrier is going to be cosine 2 pi FCT. That is a cosine we use. That is a carrier we use. Simply, we just multiply our message with the carrier, and then you transmit. So this ST, this is what we transmit over the air. This transmit signal is actually just simply multiplication of message and carrier. Sometimes you have some amplitude, carrier amplitude, like this. Sometimes you have that. Sometimes you don't, doesn't matter. So this AC is just constant, so it doesn't matter. Your message, MT, is multiplied with a cosine carrier. So that is a message you are transmitting in DSB, double sideband suppressed carrier. That's the transmitter, right? Very simple. So this transmitted DSB-SC signal now goes over the air, and it comes to the receiver. That's what you receive here, right? See here we have cosine times MT, message, and AC is just constant. So that is what you receive here. And how did you do in your previous receiver? You learned the DSB receiver, right? How did you do that in the last semester when you learned the DSB? What was the receiver you learned? Probably you learned the receiver like you receive ST, which is transmitted signal. You receive it. In this case, noise is not there. There's no noise. So you receive this signal ST, and right after that, you are multiplying carrier. And what is the next thing to do? You need to have low pass filter. Remember, every time when you have a mixer, you need to have a low pass filter. Right? Remember that? Why? Because we already have a cosine here, right? And you are multiplying cosine again, so you're going to have cosine square here, right? Cosine square is actually same as the DC plus high frequency. So you need to remove high frequency. That's why you always, every time when you have this mixer, you will have a filter. So once you do that, now you're going to get your message back right here. So this is a very simple structure, very simple receiver structure. This is what you learned the previous semester. But we have some problem here. There's some hidden thing here. The thing is, we assume that phase is 0. Right? That is a hidden thing. Phase is 0. So is it true that phase is always 0? No. Phase is never be 0. So this is the very ideal case where the phase is exactly matched with the transmitter. Transmitter, you can have a phase 0, but receiver also has a phase 0. That means this is a coherent detector. This is why when you learn this, you probably heard about coherent receiver or detector or communication. So you heard about coherent. So this is coherent because phase is matched. Both are phase 0. So if the phase is 0, this works. This is fine. But now the problem is phase can never be 0 in practical systems. You are going to have some random phase. In actual system, you're going to have some random phase. This is random. So now this is the problem. When you have a random phase here, right? In that case, what's going to be the output? Your output is message times cosine theta. Of course, you have some constant here, right? Just ignore the constant. Your output is going to be message times cosine theta. That's your output. So your output actually has a cosine theta, but theta is random. So that's why if the theta is, unfortunately, if it's so unlucky that theta is 90 degrees, you get nothing. If you are so lucky that theta is 0, then you get the MT, perfect signal. But if your theta is 45 degrees, then you're going to get only half of this. So what that basically means is that, let's say your original MT looks like this, right? As an example, then your output sometimes 0, or sometimes full size, or sometimes small size, sometimes 0. So depends on theta, sometimes 0, nothing. Sometimes smaller one, sometimes big one. That's what happened. But now the problem is theta is random. So you cannot make receiver like this because you are so lucky then you get this. You are so unlucky then you get this. That's not going to work, right? You cannot do it this way. So that's why what you want to do is you want to always get this. You want to get this always, all the time. So that's why we need this receiver. This simple receiver does not work in the practical system. So now let's take a look at this receiver here. We have a Costas receiver. This receiver has a little bit different structure. You see a little bit complex, right? But this is actually not complex. We already learned this. We already learned IQ, right? We already learned the QPSK. So this structure actually is same as our IQ channel, same as our QPSK structure. So here you see the I channel, Q channel. So we already learned this. So it's probably easy to understand now. So let's take a look at it. We receive this signal, ST, this ST coming in. So this ST goes up, also goes down. Now in I channel, we are going to multiply cosine. Cosine. But this cosine has some different phase. Let's call this a phi. So phi, at this point, phi, we don't know. Just let's say we have some phase. On the Q, that's what you have. And of course, you have low pass filter. So this whole structure is exactly the same as our previous QPSK I channel. This looks exactly the same. Exactly the same. On the Q channel, same way. We multiply sine, but this sine has also the same phase, phi. And after that, you have low pass filter. So when you look at this structure, so far, this structure is exactly the same as QPSK. Only difference is that in the previous QPSK receiver, we have 0 on the phase. Let's go back to QPSK receiver. QPSK receiver, QPSK receiver, see here, this is I channel, this is Q channel. In the I channel, Q channel, we multiply cosine and sine, but we assume that phase is 0. That is our assumption. So here in this Costas receiver, we have some phase. We don't know what it is, but we have some phase. So that's what we have. And you have some output from I channel and Q channel. Now, the difference comes in here. This output and that output comes in here into another block. This is a new block. This block does not exist in QPSK. This one only in the Costas receiver. This is a phase discriminator. What that basically means is this particular block try to find out the phase, try to detect the phase. We need to find out the phase. So that's why we need to have this. So this block will find out the phase rotation, and using that phase, we are going to put that signal into voltage controlled oscillator. So this is voltage controlled oscillator. We call that as a VCO. Right? So we put this phase discriminator output to the VCO. And this VCO output again goes to the cosine and sine. So this is sine. So we have minus 90 degree rotation. And then first. This is the block diagram for Costas receiver. So now let's understand what's going on here. First of all, what is a VCO? So important block here is these two. Phase discriminator, VCO. These two are the most important in this block, in this receiver, because all the other part is same as QPSK, right? This is simply I channel, Q channel, so that's not new to us, but these two are the new blocks. So what is a VCO? VCO, voltage controlled oscillator. This one has the one input, maybe you can have another input here, one output, right? So the input is voltage, some voltage. And output is frequency. And this one sometimes has another input, that is a reference frequency. And in this particular case, right, what we're going to have is that we are going to have the reference frequency FC. FC is a carrier frequency, so that's going to be our reference frequency. And the input is voltage, and output is a frequency. And how things work is this voltage, input voltage, can be sometimes positive or sometimes negative. Okay? if the voltage input is 0, okay? If the 0 voltage is coming in, then the output is same as FC. Okay? So this reference voltage comes into the frequency output if the input is 0. But if the input is positive, let's say input is some positive, then this frequency output is, let's say this one, let's say input is some plus delta voltage, just example, right? Delta can be any value, maybe 0. For example, right? Maybe 0.2 voltage, or sometimes 2 voltage, right? 2 volt or 0.2 volt. Some positive volt comes in to the input. Now the output is going to be a little bit higher frequency, right? So let's put the input-output relationship here. So this is the input voltage. You have an output frequency. If the input voltage is 0, your output frequency is the same as a reference frequency. If your input voltage is plus something, this is just an example, right? This is just an example. 0.2 volt, now the FC plus some delta. And if the input voltage is plus 2, then maybe this is like something like this. If you have some minus voltage comes in, then your output frequency is going to be something like this, right? If you have some big minus voltage comes in, your frequency is much slower than this. So do you see the idea? The idea here is that let's draw the input voltage here. Let's think about input voltage. Input voltage, this is time domain. If the input voltage goes up, goes down, goes up, stays 0, goes up. Let's say this is the input voltage. If the input voltage goes up to the positive, sometimes go on to the negative, and sometimes flat to 0, something like this. Now let's look at what is going to be the output here. Let's say this is time domain, and output frequency is going to be like, let's say this here, let's say this is output. The y-axis is the output frequency. This is FC. Output frequency also goes up, goes down, flat, and goes up. And here maybe it's FC plus delta. Here is some FC minus some another delta too. Do you see what I'm saying? Simple, very simple, right? If the input voltage goes positive, right? Some positive voltage comes in. Now the frequency is getting a little bit faster, getting higher. Frequency is going higher. And if you have a big positive frequency, then the frequency is getting even higher. Okay? And if the input voltage goes to negative, small negative, then the frequency is getting a little bit slower. If you get a big minus voltage comes in, your frequency is getting much slower. So that's what it is. So this is linear, basically linear, right? If a voltage is 0, your output is same as this. If a voltage is positive, meaning higher voltage than 0, your frequency is FC plus some other frequency. So frequency is going up because positive voltage comes in, your frequency goes up. Okay? Negative input voltage, your frequency goes low, goes down. Simple, very, very simple. So that's what it is. This is why we call this voltage controlled oscillator. This is eventually an oscillator because we are creating frequency. But this is not simple oscillator. This is controlled by voltage. If we change the voltage, we can make different frequency. Right? If you want to use the reference frequency all the time, you can just ground this. You can put this one into 0. Then you always get reference. But let's say I want to create FC plus, let's say our FC is 100 megahertz. And what I want to do is that I want to create 100.01 megahertz. So it's a little bit up, right? A little bit higher. How do you do that? You're going to put a little bit of plus voltage. Okay? Just plus voltage, constant. Then your output is going to be a little bit higher. So you can make your own frequency based on voltage. Okay? That's what you want to do. So that's the output. So that is a VCO. So what's going to be the input to the VCO here? That is the voltage. So this phase discriminator basically detects this signal here from the I channel and that signal from the Q channel, right? And what's the output here? What is the output here? This output, I told you here already, right? If you have some, for example, this part, I channel, this I channel looks same as this Costas, this coherent receiver. Basically same, right? This one and this one same. So when you have some phase difference, your output will always have MT cosine theta. Same here. In this case, we have a phase difference. We have a phase of P. Because of this, we're going to have MT cosine phi. From here, you're going to get MT sine phi. Now the question is, we want to detect phi, because phi is the phase difference. If we can make a phase 0, right? If we can make phase, this phi become 0, it's perfect, right? So that's what we want to do. We want to find out phi. That's our goal. And we know that the output from I channel looks like this. Output from the Q channel looks like this. So now in this block, we want to find out the phi. How do you do that? How can you find out the phi? We have two inputs. Yes. We can use tangent equation. Because we get cosine here. We get sine here. So how do you do that? Now what you want to do is you want to divide this one by this. So we have two inputs, right? One input, MT sine phi. We have another input, MT cosine phi. So we have two inputs, right? So inside this phase discriminator, what we want to do is we want to divide. Simply divide. Once we divide, this cancels out. Now what is this one? This one is same as tangent phi. And what we want to find out is phi. So what do you want to do? Phi equals arctangent, some value. Right? That's what we want to do. We are going to use the arctangent, and then we are going to find out the phi. And that phi, we can calculate the phi. This phi will go into here, and your output is going to be tangent inverse. Not this one. We are going to simply, we are going to calculate this one, right? When you calculate this will become some value. When you do division, it's like this, right? When you do MT cosine phi, this is just a mathematical representation. You're going to get some value, right? You're going to get some value like this. From here, you're going to also get some value. Eventually, this is just a mathematical notation. You're going to get some value. Eventually, you're going to get some value. So you just do a division, then you're going to get some value, right? So the phi equals arctangent of this value. So using that value, and put that in here, that's going to be your voltage. So that voltage goes into here. So let's say if you're, let's think about the very ideal case. We are very, very lucky that phi equal to 0. Then what's going to happen, the whole thing? If the phi is 0, if everything is very lucky, this output is going to be 0. You get 0 output, right? You get 0 output. So when you do division, this output is going to be 0. Oh, I'm sorry, this is 0, right? This is 0. So you get 0 here, right? So since you get 0 here, your output is going to be 0. So if your output is 0, then what's going to be the output from VCO? Reference output. So your output is FC. So everything is good because we already using FC, and output is again FC. So everything is good. FC output, you get 0. So that's what we call as a locked up. We have this VCO, this root. This is iterative, right? It's keep doing continuously. And once this one is fixed into FC and phase 0, we call that as this is locked, because we go into the very steady state. So it's locked. Okay? So that's what we want to do. Now let's think about this way. Now phi is not 0. That's what's going to happen most likely. Phi equal to not 0. Let's say phi is a little value. Let's say phi is like a 5 degree. Just an example, right? If you have phi equal to 5 degree, very small value, again, we calculate this, right? In that case, this empty sine phi is going to be very small value, because sine 5 degrees is very small, right? So let's say this is like 0.01, and this value is going to be pretty big, like 0.99. Just an example. In that case, you are going to put this one into this calculation. Now then, we're going to do division. So we have sine 0.01. From the cosine, we have this value 0.99. So when you do division, right, then you're going to get like 1/99. And then you're going to do arctangent of that. Your output is going to be small, pretty small value. Yeah, pretty small value, but positive, I think, right? Positive. Positive, I don't know, maybe positive 0.005 volt, something like this, right? Very small voltage, positive, very small voltage comes out. Now what's happening is you are not going to get 0. You're going to get very small positive value into the VCO. So now what is the output of the VCO? Your output of the VCO is not FC. It's going to be FC plus tiny hertz. It's a little bit higher than FC. A little bit higher. In that case, what happened? This is continuously running. So let me show you what happened here. Let's say this is FC. Maybe our FC is 100 megahertz. Let's draw the FC here. Something like FC is this kind of frequency. Let's say this is our FC. Okay. Now, after this iteration, our new output, new VCO output is going to be a little bit higher than FC. So a little bit higher frequency means a little bit faster fluctuation, right? That basically means suddenly sometime your frequency is changed. So your frequency is a little bit faster. Okay, that's what they mean. Then why do you want to do this? Here's what that basically means. This case is that we have a phase difference of 5 degrees. That basically means, let me use this diagram here. Let me draw the picture. Okay, let me draw the picture here. this one, right? This 5-degree phase difference basically means that the carrier frequency used in transmitter and the carrier frequency used at the receiver has a different phase, right? This blue one is the carrier, TX carrier, let's say, and the red one is RX carrier. If both one are exactly matched, meaning coherent, in that case, the TX carrier looks like this. This one is cosine 2 pi FCT. And RX carrier is again 2 pi FCT plus theta, some phase difference. But if the theta equal to 0, that means it's perfectly matched, like this, because phase is matched, right? That is the case of coherent. However, if theta is not 0, that basically means that the TX carrier looks like this. This is a cosine 2 pi FCT. But RX carrier has the phase difference, like 5 degree or some 10 degree. So it's a little bit off, like this. That's what they mean, right? Because we have a little bit of phase difference. That's what they mean, right? So this is what's happening. Now the problem is this theta is random. This offset is random. But this is what's happening. And what we want to do is we want to detect how much theta we have, and we want to correct it. We want to make it synchronized. Now the question is, how do you make them synchronized? How can you make it? Let's say theta you can find out here by doing division, right? You can do arctangent, you can calculate the theta, no problem. But now, let's say theta we can find out, then how do you correct it? That's the question, right? The only way to correct is to change the frequency. That's why we are using this VCO, and depending on the output, we are changing the frequency. Sometimes the frequency is getting faster, sometimes getting slow. So let me tell you what happens if we change it. So we have this red one. Red one is a receive carrier. If we find out that we have this theta is the phase offset, if we have this offset, right? If we cannot correct it, then we always have this offset. So now, if you want to correct it, now what you want to do is that you need to make this red one a little bit faster. The frequency is a little bit faster. Why? Let me tell you here. This one. Which one has a higher frequency? This one is a higher frequency, right? When you increase the frequency, that means it's getting faster, right? So let's make red one a little bit faster. Okay. Now the red one is not FC, but FC plus delta F. I want to make a little bit faster. In that case, it's like this, a little bit faster. So eventually, it's getting a little bit faster, eventually it'll match. Eventually it'll match some point. Do you see my point? So if the frequency is the same, then this offset will never match, right? You always have this theta. But if you can make this red one a little bit faster, initially you have a little bit of the offset, but red one is running a little bit faster. So eventually it'll catch up. Okay? Eventually you catch up. Once you catch up like here, now what's happening? In this loop, once you catch up, your phase at that point becomes 0. So at that point, because this is running continuously, this output becomes 0 at that point. So that means we're gonna lock it. Once you lock it, your frequency is FC. So only up to catch, you're gonna make it a little bit faster. Once you catch it, now we could go back to FC. So we are going to perfectly match and go on like that. Do you see my point? So that's what's happening in this VCO and in this structure. Okay? Yeah. So that's what's happening. Let's move on to next slide. So based on that, now this is a BPSK receiver. So the previous BPSK receiver we saw was a very simple structure, right? Let's go back to the previous BPSK. So this is the BPSK transmitter receiver we learned, right? In this receiver, right? In this BPSK receiver, there's no way we can detect the phase, and there's no way we can correct the phase. So this receiver is so simple. So if you have some phase difference, we cannot do anything, right? So simple receiver. So better receiver is this one. So this is a better receiver in BPSK. Transmitter is same, same transmitter. But receiver, we're going to use Costas receiver for BPSK. So once you use this Costas receiver in BPSK, so this block diagram is same as the previous slide. So this one is same as this slide. Okay, same thing. So once you use this Costas receiver structure in the receiver, in the BPSK receiver, what's happening is even though you have phase difference, this phase difference is random, right? This data can be big or small. Even though you have a random phase, that's okay. Because this one goes up, this one goes down, and eventually your output here is going to be cosine phi. Actually, this is, okay, let me change that. This is not phi, actually. This is a cosine theta plus phi. Sine theta plus phi. Yeah, because the noise, the channel already have a phase difference theta, and internally we are making another phase phi. So eventually those are combined. So that's the phase error. We want to make this phase error to be 0. Right? That's what we want. So anyway, since we have a phase difference, that phase difference will create some output here, voltage output, sometimes positive. If that means positive, right? If that is positive, what does that mean? That means like this, right? That means red one has to run faster in order to catch up. But some other times this happens, right? Let's say transmitter carrier has this, but receive carrier has this, right? We have this data. So compared to these two, right? In this case, the red one is behind. This one, red one is on the front, right? That's difference. In this case, what do you want to do? In this case, again, we want to change the frequency of the receive one. So let's change the frequency of the red one. In this case, what we want to do is we want to slow down. We want to reduce the frequency. So we want to slow like this, slow. Eventually, it'll catch up. Once you catch up, then it is locked. Then we're going to get 0 output here. 0 output will create the FC frequency. So after this, we're going to have same FC. Okay? So in this case, what's going to be the output from discriminator? You're going to get negative voltage. In this case, right? You're going to get, from this, you're going to get negative voltage. You get a negative voltage, so your output is going to be, your output frequency is lower than FC. Like this, right? This red one has a lower frequency than FC. So that means you slow down. And once you catch up, it is locked. So keep running, continuous time, keep running. So this output is continuously changing. Your output frequency also continuously changing. So that's how you catch up. And eventually you're gonna match the phase. So once you match the phase, like this, right? Then it also match because we locked in and FC is the output. Okay? So that is the structure of Costas receiver. So again, this picture is from analog, right? We learned the DSP, SC. And when you learn the DSP, you already have this in your book. And right now we are learning the digital communication, but the same structure is used for digital communication. So analog digital in this case is same. So we are going to use this structure to detect the phase. So once you detect the phase, that output becomes a voltage, maybe positive voltage, some negative voltage. That voltage will change the frequency. So that way we eventually are going to catch up. And once we lock in, then we are good. Okay? Since this is a BPSK, right? Ideal scenario is that you're going to get 0 here. From the Q channel, we want to get 0. Because we want to make this phase error to be 0, right? We want to make this phase offset to be 0. If this phase offset eventually will be 0, that means your output from Q channel is going to be 0. That's why we are not going to get any output. We are going to get only output from I channel. This Q channel will give you some information, just information to correct this, to detect the phase. We are not going to use it. We're going to use it only, you're going to use only the I channel, the I output from the I channel. That's what we're going to have. And eventually we're going to decide, is it positive or negative? And depending on that, it's going to be 1 or 0. That's the output of BPSK. Okay? So that's a BPSK receiver using Costas receiver. Let's take a look at the QPSK. In QPSK, the same structure is used. We have a QPSK transmitter here. We have a QPSK receiver. So this receiver actually looks almost the same as our previous QPSK receiver. So let's compare here. So this is the picture for the QPSK receiver we learned, right? We already learned the QPSK receiver. But in this QPSK receiver, there's no VCO. There's no phase discriminator. So if you have a phase difference in the channel, this structure has no way to detect the phase. Okay? So this receiver is a very simple receiver with ideal case. If the phase difference is there, this is not going to work. So that's why the better receiver is this. This looks similar because we have still I channel, Q channel, almost the same. Only new things is phase discriminator and VCO. Right? This is the new block. You need to have this, like Costas receiver. So how it works is same. You have a cosine here. Again, cosine phase difference coming in from I channel. From Q channel, you have a sine phase difference. Bring this together, and you are going to calculate the arctangent calculation. And your phase output, phase error, will go into here as a voltage, and that will create the new frequency. Sometimes you're going to make a higher frequency, sometimes low frequency, same way. So eventually when you run like this, right, then eventually this phase difference should be 0. Phase output to be 0, right, eventually. No, actually. In this case, eventually your phase output is not 0, actually, right? Because the phase output in this case, okay. In BPSK, let's go back to BPSK. This is BPSK. In BPSK, when you look at the constellation, we always use this one or this one. So this is a +1, like S1 symbol, S0 symbol, -1. So we know that BPSK, we used only these two, right? This one, our original symbol is phase 0. This one has a phase 180 degree. So we know this, right? That's why eventually we want to make this phase difference to be 0. That way we are going to just detect +1 or -1. But in QPSK, in QPSK, our constellation is different. In QPSK, our constellation is here, 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 here. And this one, let's say, is a 45 degree, 135 degree, something like this, right? So eventually, the phase difference here, again, the phase is random, but eventually, we want to make this phase to be some number, like 45 degree, 135 degree. I think that this block diagram, I think a little bit wrong, right? I think this is a little bit wrong, I think. Because when you have, if you use the same phase discriminator as in BPSK, now then when you have some phase difference, you're going to get some voltage output, right? That will kick in some higher frequency. So that means, I think this one's a little bit wrong. But the idea here is, in QPSK also, you can combine these two and find out the phase difference. And based on the phase difference, we can change the frequency in order to catch up. But in this case, we don't want to get the phase 0. We want to get one of these phases, maybe 45 degree or 135 degree. So that's what we want. And we want to do that. What we can do is we can do this way. Something like this. This is just hardware. So if you do it this way, right? If the phase difference becomes 45 degree, that means this one becomes 0 also, right? If you make this one phase difference to be 45 degree, that means this becomes 0. Once this becomes 0, then you're going to get 0 output. 0 output means we locked up, right? We're going to lock, so we get FC. So that's the idea. In QPSK, we don't want to get 0. We want to get 45 degree, because that's where we have symbols. Okay? So simply speaking, we want to make synchronized. We want to make our phase to be synchronized with the transmitter receiver. But because of this random phase in the channel, we need to use this Costas receiver structure. Okay? And sometimes you need to make a faster frequency or a little bit lower frequency. That way, we're going to correct and make it aligned eventually. Okay? That's the idea. Okay? Okay. Yeah, I guess we can continue this one next time.